Thank you, and good afternoon, everybody. Thank you for coming to Anna's talk. So it is my delight to welcome Ana Chies-Santos. She is an associate professor at the Federal University of Rio Grande School, often abbreviated UFRGS, which is in Porto Alegre, Brazil. And Ana got her PhD from the University of Utrecht in the Netherlands, and she was then a postdoc at the University of Nottingham for 3 years. She has been at her current post at UFRGS since 2015, and she was awarded the L'Oreal UNESCO ABC Prize for Women in Science in 2018, and was also elected an affiliate member of the Brazilian Academy for Sciences for 2022. She spent her sabbatical year in China at the Shanghai Astronomy Institute. So I'm very happy to be able to give her introduction, because the first time I met Anna was during the COVID lockdown when she was giving an introduction for me. So, thank you.
That's true. So thank you, Mike, for the kind introduction. So it's a pleasure to be here today to speak to you about one of my favorite subjects, globular cluster systems, or how we can use globular clusters to probe the buildup of their host galaxies and their environments. So this is, okay. It's not gonna. So this is one of the lines of my research group, Extragalactic Archaeology and Transformation of Galaxies group in Porto Alegre, over here, in the last state down in Brazil, next closer by to Buenos Aires in Argentina, then to more famous cities you might have heard of, such as São Paulo and Rio de Janeiro. As Mike said, the name of my university is quite hard to pronounce, and all the universities in every state in Brazil has a federal university, and they all start with UF, which means Federal University, and they have these unpronounceable acronyms. And at URGS, we are one of the few places that has an undergrad degree in astrophysics, and some of the work I'll be presenting today I did together with some undergrad students that later were master students. So these are some of the faces in the research group. And part of the group focuses in finding and characterizing galaxies undergoing transformation, especially jellyfish galaxies. But this is not what I'll be talking to you today. I'll be talking about work on early type galaxies and late type galaxies, more well-behaved, and their globular cluster systems. And these are some of the grad students that are working on this, together with my colleague Cristina Furlaneto. And these undergrad students here that I supervise together with my colleague Charles Bonato, and work in close collaboration with Juan Caso in Argentina, and also have here in France. And also we have, I'll be presenting some work from Eduardo Hartmann, my previous student that is currently applying for PhDs. So I'll give a long introduction of the fields of globular clusters, starting from the Milky Way, local group galaxies, GC systems and their environments, talking about galaxy masses, and I'll show some of our past work on this. And I'll focus on these works that are recent or are currently being done on globular clusters and their relic galaxies being their hosts, and globular cluster systems in spiral galaxies that are surprisingly neglected in this field, and especially focusing on a recent paper on the M81 triplet, very nearby. And I'll finish off by showing some work on globular clusters around low surface brightness galaxies, very nearby as well, around 10 megaparsecs. And I'll show prospects for the field with current and future facilities. So I hope by the end of this talk, I should have convinced you how important globular clusters can be for the topic of galaxy formation and evolution. So we all know that talking about galaxies, we all know that galaxies form hierarchically, and they're the byproduct of successive mergers and accretion events. And at the core of this hierarchical growth paradigm is the agglomeration of mass in galaxies by mergers or accretion that will bring about structures that are as beautiful as this one in this image. And how can we understand the fate of a galaxy to become such as the one as in the last image, as stars, gas, and dark matter, they all scramble, and that erases traces of the progenitors and of the process that occurred prior to or during these events. And objects caught in the act of merging and just after a burst of star formation are quite rare in the local universe, and we have to often be guided by simulations. So we need to go out there and search for a population of objects within galaxies and their environments that can help us testify to a combination of different progenitors and to any new star formation that occurred as part of this growth process. And these are the globular clusters. There are these old stellar groupings held together by gravity, such as this one, this very metal poor globular cluster, actually the most metal poor one in the halo of the Milky Way, as seen by the J+ survey, which I will talk more about in a bit. Globular clusters are very bright. They present from 10 to the 5 to 10 to the 6 solar masses, and they're present in almost all galaxies. And globular cluster formation accompanies major star formation episodes in galaxies. And GC seen at distant galaxies, like these ones, are lighthouses that allows us to study their host parts out to large distances. Globular clusters drive a broad range of science cases, which I will not be able to cover. Otherwise, I'm never going to finish this talk in 45 minutes. But they have been claimed to trace dark matter in galaxy clusters and in galaxies, and they're probes of the extragalactic distance scale, and they're sites of stellar evolution and high energy astrophysics. So GCs are found in almost all galaxies, but in different numbers. Dwarf galaxies will present from none to tens of globulars, spirals from tens to hundreds, and ellipticals hundreds to 10,000s. If we look at their color distributions, we're going to see that the color distributions vary from host galaxy luminosities, with lower luminosity galaxies hosting almost exclusively blue metal poor globular clusters, while higher luminosity galaxies will have this traditional bimodal color distribution, hosting both metal poor and metal rich, or blue and red globular clusters. And if we look at the color or the metallicities of both these red and blue peaks, we're going to see that they correlate with host galaxy luminosity, with dwarf galaxies, metal poor globular clusters being more metal poor than the metal poor globular clusters of more massive galaxies. And compared to other stellar systems, here we have this plot of the absolute magnitude in the V band versus the effective radius, and we see the globular clusters lie around this region. They typically have a size of a size distribution that peaks around 3 parsecs, and the globular cluster luminosity function has a turnover at about -7.4 in the V band. And they can be confused with ultra-compact dwarf galaxies, which have been found in surveys of globular clusters. But these UCDs, they have a higher mass to light ratio that could not be accounted for just by stellar remnants. Thus, they should have dark matter, and thus they should be galaxies. And we have a separation between star clusters and galaxies. So the field of globular clusters can be divided basically into two: the field where we study resolved clusters and unresolved star clusters. In the resolved part, we look at the individual stars and study their properties with the usual techniques. And for unresolved clusters, we have to look at the integrated light and look at it as the sum of all the stars in the cluster. And for that, we have to make use a lot of stellar population models. In the Milky Way, globular clusters are found in the bulge and the halo. And as seen by Gaia, here we have the distribution of globular clusters in blue and their pathway over the next 10 million years from this work of Helmy and collaborators in 2018. And in red, we see dwarf galaxies that are satellites of the Milky Way. And let's focus on these two guys here, a metal poor and a metal rich cluster, and look at the distribution metallicity of the globular clusters. And what we have is a blue and a red peak with very few of intermediate metallicity. And what about their ages? We know that their ages are around or older than 10 billion years with a lot of uncertainty. And here I'll open up a parenthesis to talk about one phenomena that has been around for quite a while, and we don't manage to solve, which is the phenomenon of multiple stellar population in globular clusters. And this is the only part of the talk I'll be touching upon things related to resolved stellar populations. So as simple stellar populations, we expect globular clusters to, when put in color magnitude diagrams such as these ones, to have single sequences. But in reality, when we look at them in enough detail, we see multiple sequences. And there have been many models and scenarios put forward, and they all fail in some way or another. And we touched a bit upon this issue, looking at 5 globular clusters, both from the J+ and the S+ survey, the J+ in the north of Spain, and the S+ in Tololo in Chile. And what we looked at, we tried to leverage on the wide field of view of these narrowband surveys that have actually 12 bands. And some of them were quite useful to select at least the two main stellar populations in the RGB. And we did that, and we ended up finding more and adding more noise to the whole picture in the literature as we find conflicting results with other studies, and the radio distributions, they behave differently when we compare the outskirts of the cluster to the centers of the clusters. So what we really need is a survey that is homogeneous and goes very deep and reaches out to main sequence levels and even below. So closing the parenthesis. So going back to unresolved stellar populations. So how do we learn about ages and metallicity content, taking spectra and images at different colors? And let's focus here on these two galaxies, our satellites, the SMC and LMC. They have a few old globular clusters, some of intermediate age, and some that are just a few million years old. The clouds also host many star clusters that are much younger. such as the Taranto Nebulae, but it's not regarded as a globular cluster per se. And the Magellanic Clouds also have suffered quite some interaction between themselves and the Milky Way halo. And as we can see in this H1 image and these simulations, and these interactions supposedly have formed a bridge of gas and stars. And here we see the bridge of gas. And there exists a population of star clusters in such a bridge. And here is some recent work of a PhD thesis I was recently a committee at. And we see that the bridge stellar clusters, this work from Oliveira this year, shows that the bridge star clusters seem to have formed during a collision that happened 200, 300 million years ago. And there seems to be some degree of ram pressure stripping besides tidal forces happening here. And this is quite interesting, as this is exactly the age ram pressure stripping is supposedly acting in galaxy clusters to form the jellyfish galaxies in other environments. Now let's go to our spiral neighbor Andromeda. As it's the case for the Milky Way, where the globular clusters are in the bulge and halo, in M31, besides being in the bulge and the halo, they are also heavily associated to streams, as can be seen in this beautiful image from the PANDA survey from Mackie and collaborators, where we see the velocity of the globular clusters color-coded by this bar here. They are heavily associated to the streams. What about the metallicity distribution? We have that compared to our galaxy, the Milky Way, the GC system of Andromeda has more of a continuous distribution with lots of clusters of intermediate metallicity. And Andromeda also hosts the most metal-poor globular cluster ever found, X8, that is 1/800th of solar metallicity, exactly minus 2.9 dex, and this was found in 2020 by Soren Larsen and collaborators. And it's also extremely magnesium depleted. And the last thing about our local group before moving forward, the Fornax dwarf spheroidal hosts 6 very metal-poor globular clusters, and they're more metal-poor than the bulk of the stars in this galaxy. And here you can see their distribution around Fornax and the HST images. So moving on to early type galaxies, such as these two here at the center of the Hydra cluster. These galaxies, NGC 3311, will host about 15,000 of point-like sources, and most of them are regarded as GCs. If we go to other galaxy clusters and Fornax, Virgo, and Abell 1689 galaxy cluster at redshift 0.18, we're gonna see the globular clusters are not only associated to the halos of their host galaxies, but also free-floating around in the galaxy cluster, and they're called intra-cluster globular clusters. And in this image that used to be, I think it still is, the deepest HST image ever taken, they found Blakesley and Tadla Alumno found around 200,000 globular clusters. And when the first image of JWST came out, I guess all extragalactic astronomers stopped and wondered. And I was particularly impressed with the amount of point sources that were around this central part. I did post on Twitter when it was still Twitter and not X, and I got only 4 likes. But anyway, we saw later on there were a couple of papers in the archive. They're now accepted, where they analyzed carefully the star cluster, well, the GC system, the point sources, and concluded that the majority are in fact globular clusters, like these point sources here in the standard DS9 regions that we can see. Another case that has sparked a lot of debate recently is the Sparkler galaxy at redshift 1.4. This one here that seems to harbor many metal poor globular clusters, and when people have measured ages, they seem to have ages overlapping with the metal poor sequence of local group galaxies. And here is a plot, the age metallicity relation from Angela Damo and collaborators, where they did this analysis, and they see a large metallicity spread at younger ages, especially. And they claim that this could be evidence of a recent merger, and this could also explain why the globular clusters are located around the main body of the galaxy in a configuration that is also observed in redshift 0 galaxies. And even more recently, there was this paper on Abel 2744 at Z.3 from Bill Harris and Marta Reina Campos, where they looked at the point sources and concluded that they were most likely globular clusters and estimated their GC masses as systematically higher than in present-day galaxies, and that would be consistent with a large normal globular cluster distribution, but seen 3.5 billion years before in dynamical evolution. And it seems that the spatial distribution of the bluer clusters, more metal poor, should resemble the gravitational lensing map of the cluster, and this is consistent with recent observations I'll mention briefly. So now let's have a look at GC systems and galaxy properties that are well known. But first, let's talk a bit about the cartoon picture of the two-phase galaxy formation. For massive galaxies where we have an in situ first phase that happens at redshifts greater than 2, followed by a second phase dominated by accretions that happens since redshifts of 3. And this first phase would form the supposedly called in the literature red nuggets. And if we let it evolve, we'll have in the last 8 billion years, this second phase dominated by dry mergers. And if we let it coalesce, we'll get a massive elliptical we see in the nearby universe. And this is supported by the size evolution that's well known for many years already. And one way to study globular clusters in these galaxies is to look for red nuggets that evolved passively, kind of frozen, and they're like time capsules of redshift 2. I'll talk about them in a bit. So how do we add globular clusters to this second phase, two-phase galaxy formation model? We have that I showed before that the color distributions of GCs are typically bimodal in massive galaxies, and in we'll have this first in situ phase that will form the red clusters, and the second phase will bring in the blue clusters by accretion. And this is consistent with if we compare, for instance, the age metallicity relations of the SMC and the LMC with the globular cluster system of the Milky Way, we see that the age metallicity relations of our satellite galaxies are consistent with the distribution here of the metal poor globular clusters in the Milky Way. So they are consistently accreted from dwarf galaxies. So what do simulations tell us about globular cluster formation? Well, that it happened in a turbulent environment at high Z. And we have many simulations, and there's been a huge advance in the field in the last years. We have the E-mosaics paired with Eagle, fire and semi-analytic models. And more recently, there's a catalog of globular clusters for the post-processed illustrious TNG50. And here is one example of the E-mosaic simulation paired with Eagle, where the gray shading will show the gas fragmenting, forming stars and falling onto the central galaxies. And the GCs are then indicated by these colored dots, and the different colors represent the different metallicities. And in E-mosaics, they have about 23 halos, and these are all Milky Way sized halos. And we see that mergers and accretion will bring on new globular clusters to have many different configurations, as we'll see later on, of the age metallicity relation. And E-mosaics also predicts that the formation histories of GCs peaks at about redshifts 2, the same way as star formation in galaxies. And I'll also mention here other possible sites of GC-like object formation. The major mergers such as the antenna galaxies, the antenna galaxy that has been known for quite a while, here 2002, that forms clusters that are very massive, and they're called young massive clusters, and they're very metal rich. And more recently, we see in the tails of strong ram pressure stripped galaxies, such as these from the GASP survey, many clumps. And these clumps tend to have stellar masses of the order of 10 to the 5 to 10 to the 7 solar masses. And these are consistent with proto-GCs or even UCDs, but then without the dark matter. Moving on and talking about the total mass of GC systems compared to the parent galaxy stellar mass over here, and the dark matter halo mass. Sorry. So we see that there's GC systems are connected to the properties of their host galaxies and show a direct linear relation with the dark matter of the parent halo galaxy. And this is not the case so much for the stellar mass. Let me have some water. And another thing that has appeared a lot in the literature recently is that we can use the number of globular clusters to constrain the total mass of the host galaxy, of course, with a lot of scatter. So this has been used a lot for to try to derive masses of low surface brightness dwarf galaxies that host GCs. So if we count GCs, we may have a lower limit to the total baryonic dark matter mass of the galaxy. And very recently, we have these claims from, I'll show here the example from the E-mosaic simulation from Magda Reina Campos, where she claims that we can constrain the shape of dark matter halos with GC. So here we have the projected surface density maps of dark matter and the number density map of GCs. And they claim that they recover tight relations between the profiles of GC number density and those of dark matter. Thus, the profile of dark matter could be accurately recovered from globular clusters. And here is a very recent paper by Diego and collaborators, where they look at the dark matter lensing map and compare with the globular cluster distribution number density in blue and the dark matter in yellow, and they claim there is some correlation. What about ages? We talked about metallicities, dark matter. What about ages? Observationally, I mentioned there already that they're mostly older than 10 billion years. And we do this, these measurements, very careful analysis of spectra and images of different colors. And I've done that in the past. even with 3 bands. But having lots of bands, things get easier. So ideally, we would like to have spectra for each object we study, but with spectra we can measure the strengths of different lines and compare to stellar population models. But imaging will cost much less, and with less observational time invested, we can get colors of several objects in one go. And this is what we did in our recent paper. And here I have the spectrum of the Sloan of one given M81 globular cluster and the J plus spectral energy distribution of the same cluster. So having less bands, and the less images, we can still use these color diagrams and still have some constraints on ages and metallicity. And there has been some claims of varying color relations according to location within the Virgo cluster. So here we have the projection in the sky of M87 globular clusters and other globular clusters color-coded to the different distance from the center of M87 and to the center of their host galaxies. They're all early type galaxies. And here we have the color plots and the Milky Way globular clusters are in black here. And we see that the Milky Way relation fits much better. I mean, doesn't really fit, but it falls much better within the color plot of early type galaxies that are far from the center of the cluster. And we did some work on this as well, revisiting the Virgo cluster, also with near-infrared imaging, and extended it to the Hydra cluster. And this was the subject of a PhD thesis. Okay, so another relation we have for GCs, the number of GCs normalized per host galaxy luminosity, MV minus 15, is the specific frequency, which can be, when plotted like versus the galaxy luminosity, we can see it's high in both giant galaxies and dwarf galaxies, but seems to be low at intermediate luminosity galaxies. And the GCLF, the globular cluster luminosity function, is kind of like a cosmic cape, as it's we define it as the relative number of GCs per magnitude and use it as a standard candle for extragalactic distance determinations. And the GCLF can measure distances to galaxies within uncertainties of 10%. And as I mentioned already, the GCLF of the Milky Way has a turnover at minus 7.4 in MV. And as we go further out in distance, we will start sending less and less fainter GCs, but the turnover magnitude seems to be maintained at the same value. So now I stop with the long introduction, and I'll touch on these 3 projects I talked about. First, on relic galaxies and their GC systems. So relic galaxies are compact, massive, red, and they present old stellar populations. They're outliers from the mass radius relations, such as these guys here in less than 100 megaparsecs away. And one interesting case that appeared a few years ago was NGC 1277, a galaxy in the Perseus cluster that seems to contain almost exclusively red globular clusters, given by this orange histogram. And when compared to other Virgo cluster galaxies with the same colors, the color distribution here in green from ACS, VCS survey galaxies, that they present both blue and red clusters. So this would be another evidence for this galaxy being survived red nugget. And we did some work together with a former postdoc, Carla Lama Martinez, on a sample that was in the JWST archive. And they're all outliers from the size-mass relation. And we extracted the GC systems and analyzed their I-H colored distributions, which are not the ideal distribution, ideal colors, but that is what we had. And we used properties such as the mean color and the width of the color distribution to compare between different GC systems. And we see that here are the GC systems we analyzed, and these two are considered stripped cases, so they're not real reds. But we find that more massive and more metal-rich galaxies have GCs with on average mean I-H colors, mimicking the effect of the GC peak metallicity galaxy luminosity relation. And we also looked at the angular momentum from cataloged already from IFU PPAC observations from Yildirim and collaborators, and compared with the width of the color distribution. And we can see some tantalizing evidence for an anti-correlation between lambda R and the I-H color standard deviation. And that would mean that successive merging events would decrease this lambda R, while the final merged system in turn would tend to have a more complex, wider GC system distribution. There's more to talk about here, but I want to mention the other works. And with this former undergrad student, we looked at relic. We looked for relic galaxies in Illustris PNG, and we found 5 good cases and 2 great cases that really looked at like the ones observed from the Yildirim and collaborator sample. And this first subhalo seemed to be a satellite in a dense environment, just like in GC 1277. It is close to the center of the most massive cluster in the simulation and has a very low dark matter to stellar mass fraction. And later on this year, there was a study by Trujillo and collaborators. They also found the same thing for this galaxy. I forgot to put the reference. And the other case, the other subhalo seemed to have evolved more in isolation. And anyway, we find these relic analogs seem to be formed in massive halos than other quiescent galaxies with similar stellar mass at redshift 0. And recently, just this week, we submitted a paper with my PhD student where we compared, we revisited the TNG 50 supposed relics and compared to normal early type galaxies, especially the compacts, in 3 different stellar, 3 different cosmic epochs through the orbital decomposition method, which I'll not go into detail, but we find that there's a steady pathway across time that is not strongly dependent on the environment. And now Michelle is looking at the post-process GC catalogs of TNG 50. Now let's go and cover the GC systems in spiral galaxies with J+. Why do we need to go for the spiral galaxies? So there's the age metallicity relations here from the E-mosaic simulation, for example, at redshift 0 show a large variety of configurations which arise due to differences in the formation and assembly histories of these hosts. And the field of GC systems has neglected spiral galaxies because they have fewer clusters and they're hard to extract from considering the more complex background, and focused in early type galaxies. So here we having this J plus survey and the S plus as well, and trying to use the large field of view that they allowed. We looked at this M81 group of galaxies, and I'll show the results from this paper from last year. So this is the system. It's a beautiful mess. And so M81, M82, and NGC 3077. And these are 3 or 2.5 J plus fields. J plus is a small telescope, the precursor of JPAS, and it has 12 bands, and these are the bands in the optical. Oops. So in this work, we report on a list of GC candidates around these systems. And what we did, we started from a training set of 105 spectroscopically confirmed GCs. And we employed a statistical model that was customized to search for new GC candidates, taking into account missing data and photometric errors. And we searched for globular cluster twins, or objects that look like globular clusters in the parameter space that we were interested in, from being either noisy and incomplete, missing some bands. And we followed a PCA implementation that took into account uncertainties. And in 3.5 square degrees, we found about 640 candidates. And this is the field. So here's M81, M82, and the other galaxy. We have 7.2 thousand point-like sources that we started with. And in pink here, we have the 105 spectroscopically confirmed GCs. We end up with 640 GC candidates after applying the procedure I showed you before. We also made use of Gaia proper motions. And here is the color versus one of the possible colors versus the distance from the center of the galaxies. And we see that the clusters become bluer, which makes total sense. They're compatible with intra-group globular clusters. And there was a tantalizing evidence for having an overdensity of globular clusters between M81 and M82. And we also looked at a few examples of color diagrams and color distributions, and mapped the metallistic distribution function of the known spectroscopically confirmed GCs to the GC candidate ones, and they resemble that, for instance, of Andromeda. And we looked at the spectral energy distributions. They seem to, some of them seem to be compatible with GCs, the majority. And right now, I have a student that is implementing in SIGAL, the set fitting code. And he's currently using just the normal Brusois and Charlot very ancient models, but now he's implementing the new X-Shooter spectral library, and also together with our collaborator, Paula Coelho, she's making models specially adapted to J plus and JPAS. And we're finding that things are making sense, but this is work in progress. We also had 58 hours of Gemini 8 meter north to follow up these GC candidates. Quite over 20 objects were observed, but then we had one more proposal approved. Actually, it was approved 3 times, but Gemini North has been shut down because of several reasons. I hope this semester we managed to get this done. And meanwhile, the Pedros and these other students, they are analyzing a variety of spiral galaxies within the J plus footprint. We're trying to get all spiral galaxies within a given mass limit within 5 megaparsecs. And we're trying to improve the analysis and the methodology. And this is, of course, work in progress. And Mike, how much time do I have?
Yeah, so if you want to start wrapping up,
Okay.
we have the hour.
Yeah, okay.
If you want.
So I'll go quickly through this last work and wrap up. This work was done in collaboration with Marco, who has just graduated from the undergrad, and we looked at the globular cluster population and satellite galaxies around our closest S0, which is NGC 3115, located in a low density environment. I observed 2D cam pointings back in 2017, I think. And then we performed a visual inspection and structural analysis where we found 28 low surface brightness galaxies around the system, and 18 were for the first time. And these are the galaxies, and these are their colors. And we followed them up from the Blanco telescope to Gemini, and with 4 or 5 Gemini pointings, we studied we selected their globular clusters and analyzed their globular cluster distribution and GCLF. There's one guy here that is quite off, that is one that we call LSP dwarf 22, that is too close to an elliptical galaxy. And then we get it totally off. We look at the specific frequency and measure upper mass limits with the globular clusters systems for these galaxies. And now to wrap up, the prospects with current and upcoming facilities. So these are the facilities for this field that I think are going to play a major role. And to start from the ones from the ground, I'll talk I'm biased against these two because I'm part of them, but I think you're all very familiar with LSST. So I'll focus on JPAS. JPAS is a more modest project between Spain and Brazil. And it's in a 2.5 meter telescope in the north of Spain. It has finally started after many, many years. And it's made of 54 filters within this wavelength range. And this will give not a real spectrum, but the best poor man's spectrum you can get. And here is one science case for resolved globular clusters, multiple stellar population phenomena. Here we have the flux ratio between the first generation to second generation star, where we have for J plus, the U band is not the best, so it's quite shallow, and the narrow bands do not get all the filters we do not get the parameter space in the spectrum we really want. But for JPAS, this is going to be different. These two bluest bands are going to be quite good for these kinds of cases, science cases, but LSST will be even better as for the U band. And we cannot forget about the Chinese Space Station telescope. That's also going to be playing a good role here, especially at the 3 bluest filters. And from space, I talked already about the CSST, but Euclid and Roman are going to be playing a major role, but Euclid and Roman are to the near infrared, and CSST is in the optical. And here are some recent papers. This is a roadmap for LSST stars Milky Way local volume star clusters group that was recently published. And there's also a white paper outlining the synergies between Roman and LSST for extragalactic star cluster science. And there's also the Euclid one. And just to have an idea, this is the size of the field of view of CSST in red. Euclid Roman, and the tiny ones of HST in yellow and orange. So the limiting magnitudes of these surveys, such as LSST being the deepest with R27.5 after 10 years, are going to be quite interesting. But Chinese Space Station Telescope will be shallower, but from space with better resolution, reaching 0.05 arcsecond per pixels as HST. And with LSST, we will be able to probe the near complete GC systems of galaxies out to 0.05 from all morphologies and environments. Sorry to rush through this, but the take-home points are the globular clusters are powerful probes to understand the evolution of galaxies, including dark matter in galaxies and GCs in relic galaxies. I showed you a few examples of what we're currently doing on GCs in relic galaxies, GCs in spirals, and around low surface brightness dwarfs. And I rushed, unfortunately, through, but the present and near future are these photometrically, that will give photometric surveys that will give us a near complete picture of GC systems out to redshift of 0.05, considering different morphologies and environments. Thanks. Yeah. I hope I didn't go too much over time. We started a little later.
We have a few minutes for questions. So thank you, Anna, for that very informative talk. For questions. So I'd like to start with one question. So you were mentioning about Milky Way, globular clusters of Milky Way, that this is in our galaxy. There's both color populations. And I was wondering, is there any connection between that and the multiple populations within multiple chemical abundances within individual globular clusters, for example?
They all have, independent of being metal poor or metal rich, they all have multiple star populations when you look at them in detail. Even when you go to local group galaxies, you have the star clusters from the Magellanic Clouds and globular clouds. They have these splits in the main sequence.
So both the redder ones and the blue ones.
Yes.
Yeah, thanks. Rob.
You showed a few metallicity distributions within galaxies, Milky Way, other spiral galaxies, and TGs as well. I just wondered, what do the metallicity distributions of government clusters tell us about the galaxy? Is that indicating star formation history in some way? What's the differences?
So the chemical evolution, the star formation histories, and we don't understand how globular clusters form, but they, like, for instance, the fornex dwarf spheroid, why does it have a metallicity distribution that is, for the globulars, that is completely different from the stars? But in other galaxies, they seem to fit the stars. So, like, for instance, in GC 3077, that is about 10 megaparsecs away, like it fits complete. So it seems that each case is a case, but it can help us understand the buildup of the galaxy and the progenitors and these kinds of things. Don't know if that was exactly your question, but
yeah, I guess my question is, how is the globular cluster distribution? What does it tell us as a normal stellar population? I guess we're not.
Yeah, we're not. Yeah.
I was struck by the news that they all have different stellar populations because when I did undergraduate astronomy, I don't even knew this. Doesn't the fact that you have these multiple stellar populations make it very difficult to infer things like ages and metallicities from SCG? How
Yes, yeah, because the differences are not going to be that large. They're going to be million years, and the globular clusters are old, like older than 8 billion years. So if you look at the integrated light, and if you're think about billion years, it doesn't make much of a difference, but yeah. For younger clusters, it makes a difference. But so for the young massive clusters in the local universes.
More question. So you mentioned the Chinese space station telescope, and that's not one that I'm super familiar with. So what are the aspects of that that are useful for this?
It's just it's like a new HST because it will cover what all the other surveys are not covering, which is optical in space and UV in space. So yeah, having, like, for instance, for this field size information, which we're gonna get from LSST, but it's not gonna be as good. So but also we have that from Euclid, but yeah.
Thank you. I think we're at time, but let's thank Anna again